Okay, folks, last video. We're going to get into dispersion in this particular video. So there's a couple of different ways in health sciences statistics that we can represent dispersion. Just like when we did central tendency, we had the mean, the median, and mode to describe the data with a single value. So the first way in which we would move forward with dispersion is what's called the range. And the range is a very simple difference between the data set's highest value and its smallest value. So in this particular case that you see here, we have a series of 5 numbers of 10, 13, 17, 17, and 18. And so the highest number in that data set being 18, less the smallest number in that data set of 10, gives us a range of 8. When we talk about the concept of variance, which is a second way in which we can quantify and describe this issue of dispersion, we're really talking about what is the average variability of scores about the mean. So when you hear things like variance and then standard deviation, which we'll get to in just a minute, they're actually the exact same thing. It's just in the units in which they are represented. So when we talk about variance, we're talking about things in squared units. When we talk about standard deviation, we're talking about representing the variance in the original units of the metric. If we look at the formula here, you can see that that's the case. S is going to represent standard deviation, and the square tells me it's in squared units. Well, because I know the variance is in squared units, I know that this is the formula when it comes to variance because it's in squared units up front. So if we look at the squared units here, you can see that we calculate it by taking the sigma, the sum of what's known as the difference of each individual value, x. So if somebody has an x value of 2 and the average value is 1, it would be 2 minus 1 squared. So this is what we call the sum of the squares, okay? And so sigma represents the sum of the squared values. Well, what is that? The squared difference of the values, which takes each individual score, x, minus the average score for the whole sample, and then squares all those numbers. And then you take the average variability by dividing it by n minus 1. And I'll talk a little bit about what n minus 1 represents, but that's really what we call a degree of freedom. So mathematically, the variance is going to represent the average variability, or on average, how far apart is any one person in the data from the average mean value. So what the variance is going to tell us is what is the average variability of how every single person in the data set typically varies from the average value in the data set. Okay, so if we were to use the data from the previous equation, you might find that the sum of all of what's called the deviances, so deviance represents x minus x bar, the average, squared, divided by n minus 1, you would get the sum of the squares of 46 divided by 5 numbers minus 1 restriction is 4, would give you a variance of 11.5, and that is in squared units. If we wanted to get it into original units, we would then need to do what's called standard deviation, which represents the average variabilities of score about the mean in original units. So if you look at the formula for S, notice how there's no square here. It is literally the formula for variance in just taking the square root. So therefore, if we want to find the standard deviation from the variance, all that we have to do is take the square root of the variance, and we see that that reduces down to 3.39. So that means that when we have an average, the typical person is going to deviate or vary from that average by plus or minus 3.39. So how do we sort of tie all of this together? And what's the relevance of these standard deviations? Well, if we come back for a second, remember that in the parentheses here, X represents a value for the dependent variable. X bar represents the average. So we want to know, how far does one person's value differ from the average value? Well, remember, dispersion can be represented in terms of range, variance, and standard deviation. And so we're summarizing the average or the typical expected variance from each person in the data set in squared units with variance and in original units with standard deviation. But what does that mean graphically? Well, remember this curve that we did in the first video of this series, which was saying that the mean, the median, and the mode, this red line here, is always going to equal 0. And 68% of the scores in that sample are going to fall within +1 or -1 standard deviation. So if you look here, X bar, the average, plus a standard deviation, this would represent +1 standard deviation, and X bar minus S would represent 1 standard deviation below the mean. So if we were to look between this bar here and this bar here, 68% of the scores in the total sample would have their score fall within ±1 standard deviation of what we just calculated. Similarly, another 13.5% would fall above or below that standard deviation. And so 68 plus the 13.5 and plus the 13.5 would give us 95% of scores that fall within ±2 standard deviations above or below the mean. And then finally, you can see that there is a remaining 0.2%, 0.1 that goes above and below the mean. And so 99.7% of scores are expected to fall within 3 standard deviations above and below the mean. So when we hear this empirical rule, it merely means that in a perfectly normal distribution that's bell-shaped, asymptotic, continuous, and symmetrical, that 68% of the scores is going to fall within ±1, 95% of the scores is going to fall within ±2, and 99.7% of scores are going to fall within ±3 standard deviations above or below the mean. Okay. The last thing then to think about before we really sort of transition and go into lecture 3 is, how do we standardize this? So the way in which we do that is with the formula standard error, and that is equivalent to the standard deviation divided by the square root of the sample size. So if we took the standard deviation and had 3.39 divided by the square root of 5 people, we would find that at the population level, which represents the standard deviation of the population, it would reduce down to 1.52. Okay. Along the lines with standardization is this concept of what's called a z-score. A z-score is another way of a standardized score. So just how standard error took standard deviation and standardized it to the population, we could take what's known as a z-score, which calculates any particular X score in our sample and standardizes it in comparison to other scores in the population. So the way in which we would do that is by simply taking the X score, which is the person's value, minus the average value, and dividing it by the standard deviation if we're talking about it from a sample's perspective. If we're talking about it from the population's perspective, you would put it in terms of standard error, right? So in this example where we're comparing heights, it says former NBA superstar Michael Jordan is 78 inches tall, and WNBA basketball player Rebecca Lobo is 76 inches tall. Jordan is obviously taller by 2 inches, but which player is relatively taller? Does Jordan's height among men exceed Lobo's height among women? Men have heights with a mean of 69 inches and a standard deviation of 2.8 inches. Women have heights with a mean of 63.6 inches and a standard deviation of 2.5 inches, which is based off of a national health survey. So using the Z-score formula, what you're going to do is you're going to take, for Michael Jordan, the Z-score is equal to X, his height, which was 78 inches in height, minus the average height for all NBA male players, which is 69 inches. And we're going to divide it by the standard deviation, which was 2.8 inches in height. And so if we saw that, Michael Jordan was 3.21 standard deviations above the mean value, which compared to the population is significantly taller than other NBA basketball players. But when we compare it to Rebecca Lobo's Z-score, you can see that Rebecca Lobo's height is even more extreme than Michael Jordan's. So on an absolute basis, even though Michael Jordan is 2 inches taller than Rebecca Lobo, on a relative basis as compared with their peers, Rebecca Lobo is the more taller athlete compared to the people in which they compete with in the sport of basketball. And you can see that by taking Rebecca Lobo's X of 76 inches in height minus the average height of the typical WNBA player and dividing by its standard deviation, you get 4.96. And so because 4.96 is even more extreme than 3.21, Rebecca Lobo would be the relatively taller basketball player than Michael Jordan, even though Michael Jordan is actually 2 inches taller than Rebecca Lobo. So that's how you would calculate a Z-score, okay? And then the last thing to think about is what's known as a coefficient of variation. And what the coefficient of variation does is it helps to measure the relative variability of data. And so we typically use coefficients of variability to do two things: to determine which of two groups is more consistent or reliable, and which of the two has more variability. And depending upon the context of the research question, you might want to have something that's more consistent, and you might want to have something that is less variable, or you might want to have something that is less consistent and that is more variable. So it all depends. A great example that I would bring up to you is that in the case of the coefficient of variation, the way in which you calculate this with a sample is by taking the standard deviation, the average variability of scores about the mean for a sample, and dividing it by X bar, which is the average or the mean value for the sample, and multiplying it by 100. This could be done also at the population level by taking the standard error, right, standard deviation for the population, divided by the mu, the average of the population, and then similarly multiplying it by 100. So I hope this video was helpful. We covered a lot of things from frequency distributions, how to calculate them, and how to represent them graphically on an absolute basis with histograms, into a relative basis based off of pie charts. We talked a little bit about how to calculate probability. We talked a little bit about measurements of central tendency, and then we finished up this series talking about some of the different ways that we can use dispersion.